Good morning, everyone. Today, me, Nirvisa Shrestha, and Anush Pandey are excited to introduce you to one of the most important tools used to model probabilities and proportion across various fields such as machine learning, finance, and biostatics. By the end of this talk, you will understand the core properties of the beta distribution, learn how the distribution shape is controlled by two key parameters, alpha and beta, see real-world application in A/B testing and Bayesian inference, explore some underlying mathematics, and learn how the distribution helps in reaching informed decision. Now, these are the table of contents that we would introduce in this session. First is introduction, second would be mathematical formula, then shape of the beta distribution, moments and distribution properties, Bayesian inference of beta distribution, advanced application, relationship with other distribution, visualization, and conclusion. Let's get started by understanding the basics. The beta distribution is a continuous probability distribution that is defined over interval 0 to 1. This means it is especially useful when we need to model probabilities that fall within a specific range, such as the likelihood of success or failure in an experiment. This distribution is shaped by two parameters, alpha and beta, which we will delve into shortly. Now, talking about probability density function, also known as PDF, it is described as the following formula. That would be 1 by b alpha comma beta multiplied by x to the power alpha minus 1 multiplied 1 minus x to the whole power of beta minus 1. Now, in this formula, x is a variable of interest which must lie between 0 and 1. Alpha and beta are the shape parameters that control the distribution. B alpha comma beta is the beta function acting as a normalization constant to ensure that the total probability sum ups to 1. This formula is derived step by step. We start with the unnormalized form where the beta distribution takes the form of x to the power of alpha minus 1 and 1 minus x to the whole power of beta minus 1. Which indicates how the probabilities behave based on alpha and beta. Then we normalize the function by incorporating the beta function b alpha comma beta, which itself is expressed by using the gamma function. This mathematical relationship allows us to calculate the appropriate scaling to ensure that the total probability across the distribution integrates to 1. Now, the next is cumulative density function. In addition to the PDF, we have cumulative density function. While the PDF shows the likelihood of a specific value of x, the CDF answers a different question. That is, what is the probability that a value drawn from a beta distribution is less than or equal to a given value? Mathematically, the CDF is represented as the following formula, where Ix alpha comma beta is a regularized incomplete beta function which accumulates probability from 0 to the specified value of x. For example, if you want to know the probability that x is less than 0.5, the CDF provides that answer by summing up the area under the curve from 0 to 0.5. Now, the next is beta function. Beta function plays a crucial role in the beta distribution by ensuring that the total probability sum ups to 1. The beta function is related to gamma function often used in probability theory. The next one is incomplete beta function. The incomplete beta function, denoted as bx alpha comma beta, generalize the beta function, and this function calculates the area under the curve of the beta distribution up to a point x. This regularized incomplete beta function, denoted as Ix alpha comma beta, is a scaled version of the incomplete beta function. Now, let's talk about shape of beta distribution. The real power of the beta distribution lies in its flexibility. Its shape is determined by the value of alpha and beta. Let's explore how it works. When alpha equals to beta equals to 1, the distribution is uniform, meaning all values of x between 0 and 1 are equally likely to roll off your die. When alpha is greater than 1 and beta is also greater than 1, we get a bell-shaped curve, meaning there's a peak in the middle, similar to how heights are distributed in a population. When alpha is less than 1 or beta is less than 1, the distribution becomes U-shaped with probabilities clustering near the extremes, which can model extreme opinions in a survey. Now let's visualize one beta distribution. By visualizing these shapes, we get an intuitive understanding of how probabilities behave. This is a graph showing how changing alpha and beta affects the distribution. Higher value of alpha or beta creates a sharper peak, indicating a stronger likelihood around the center, while lower value of alpha or beta creates more extreme usage, focusing probabilities around the boundaries of 0 and 1. Now, in this space, this graph showcases beta distribution probability density function for different values of the parameter alpha and beta, demonstrating the distribution flexibility based on these shape parameters. The x-axis represents the variable x, which lies between 0 and 1, while the y-axis represents the probability density. Now, let's dive deeper into some key statistical concepts that help us interpret the distribution. The first one is mean. The mean of the beta distribution gives us the expected outcome based on the values of alpha and beta. It's the most likely result given the data, which formula would be alpha by alpha plus beta. Now the next one is variance. Variance tells us how spread out the distribution is. Higher variance means the outcome are more dispersed, while lower variance means they are tightly clustered. Now the formula of variance is alpha multiplied by beta by alpha plus beta whole square multiply alpha plus beta plus 1. Now the next one is skewness and kurtosis. Skewness. This measure the distribution is skewed left or right. A right skewed beta distribution, for instance, indicates the higher values of x. So therefore the formula is 2 multiply beta minus alpha root power by root alpha plus beta plus 1 by alpha plus beta plus 2 multiplied by root of alpha beta. Now, talking about the kurtosis, this shows the peakness of the distribution, whether it has a sharp peak or a flatter or more spread out shape. This would be the kurtosis formula. Now, the next is the graph. These 4 3D plots represent the behavior of skewness and excess kurtosis in a beta distribution as a function of the mean and variance.
Now let's talk about Bayesian inference. In Bayesian statistics, the beta distribution is used as a constructed prior for binomial distribution. Let's say you want to predict the likelihood of rain tomorrow. You start with a prior beliefs based on past observation. As you gather new data, you update these beliefs into a new distribution called posterior, which is still a beta distribution. This process of Bayesian updating is simple and intuitive, making it easier to revise prediction as a new evidence comes in. So there are 3 types of components of Bayesian inference. First one is prior. Prior represents the initial beliefs of assumption about parameters. For example, a probability or mean before new data is introduced. Second one is likelihood. It reflects the probability of observing the new data given the assumed parameters value. And third one is posterior. The result of updating the prior with likelihood. Posterior combines both the prior beliefs and the observation data to give a more informed and updated beliefs. Now, let's dive into this graph. So, this graph illustrates the process of Bayesian updating, which involves combining prior information with new data to update our beliefs. This graph shows three key distribution: the prior, likelihood, and posterior. Now, let's talk about advanced application. So the beta distribution has both real-world application, uh, Bayesian A/B testing. Companies use it to compare two versions of web page to determine which one performs better, continuously updating success probabilities. So the second one is machine learning. It helps in binary event modeling, such as predicting whether a user will click a button or not, updating probabilities as a new data comes in. Third one is finance. It's used in portfolio optimization to model the success or failure rates of investments, helping to predict potential returns or losses. Sorry. Fourth one is biostatics. The beta distribution is a key in survival analysis and disease modeling, helping predict patient outcome based on clinical data. So now let's dive into this graph. Each curve in the plot represents the beta distribution with a specific combination of alpha and beta, showing how this parameter affects the shape of the probability density functions, which is also known as PDF. The x-axis represents the range from 0 to 1, and the y-axis shows the density, which represents the probability of certain outcomes in this range. So now let's talk about the relation with other distribution. Gaussian distribution. So the beta distribution can be viewed as a generalization for modeling promotions which are bounded between 0 and 1. While the Gaussian distribution is defined on entire real line, when considering multiple promotions, the beta distribution serves as a more appropriate choice than the Gaussian distribution. This is especially relevant in scenarios like A/B testing or troponate data analysis, where the outcomes are restricted to specific intervals. Now, let's talk about binomial distribution. So the beta distribution is frequently used as a prior distribution in Bayesian statistics. The success probabilities of binomial distribution. When we conduct a binomial experiment, for example, flipping a coin, the likelihood of observing a certain number of success can be modeling using the binomial distribution. The beta distribution serves as a conjugate prior for the binomial distribution, meaning that if the prior is a beta distribution, the posterior distribution will also be a beta distribution. This priorities simplifies calculation and provides a coherence Bayesian framework. The uniform distribution. The uniform distribution is a specific. The uniform distribution is a special case of the beta distribution when both shape parameters alpha and beta are equal to 1. In this case, the beta distribution becomes a flat line across the interval 0, 1, indicating that all outcomes are equally likely. This relationship highlights how the beta distribution can transition into a uniform distribution, showcasing its flexibility in modeling different types of data. Now, let's talk about gamma distribution. So, gamma distribution is closely related to gamma distribution through the beta function. Specifically, the beta distribution can express in terms of gamma function. So you can see the formula of gamma function below here. This relationship establishes the beta distribution can be seen as a distribution of the ratio of two independents. Gamma distribute variables, making it practically useful in various applications involving promotions. Now let's talk about visualization. And in statistics, statistics and probability, visualizing data helps you grasp abstract mathematical concept in a tangible way. With the beta distribution, this is specifically important. This is especially important because the shape parameters alpha and beta dramatically alter the distribution appearance, and hence the insight you can draw from it. By visualizing different beta distribution, you can understand the effect of shape parameters alpha and beta on the probability distribution. Compares theoretically models to observe data to see how well the distribution fits. Interprets the likelihood of different outcomes based on how the distribution is shaped. So now, this graph showcases visualization done by beta distribution of A/B testing. So in conclusion, the beta distribution is a versatile tool for modeling probabilities within a defined range. With it shaped, controlled by two parameters, alpha and beta, the flexibility makes it valuable in applications like A/B testing, Bayesian inference, and financial modeling. By adjusting these parameters, we can model different real-world scenarios, and the distribution mean variance, skewness, and kurtosis provide insight into data behavior. Visualizing the beta distribution help to intuitively understand and interpret probabilities, making it an essential tool.
Thank you.